Okay, that whole like first 3 minutes of the video that I just made talking about all that stuff, that was muted the whole time. So the people watching the video can see me standing here, but they have no idea that I'm talking. Just awkwardly standing here for the first 5 minutes. And they missed all of that excitement. Oh well, it's fine. Okay, at least I noticed before I started the lesson. Okay, so everything is great today, clearly. Anyway, so any questions for me about time frame or what is going to happen from here on out? There was a question last class as far as like what tests there are, what things will go on your second term grade. Because we have taken a chapter 5 test and a chapter 6 test already, I'm going to add the chapter 8 test that we take next week and then your final exam. So there will be 4 tests that are all equally weighted. I'm going to equally weight your final exam on your high school grade so that I can just drop one of those 4 on your high school grade. Okay? Your UVU grade will then be, so you'll have your chapter 2, 3, 4, 5, 6, and 8 tests. But I believe they will let me, I'm looking. They haven't submitted, or they haven't sent us like the actual form that we have to fill out to submit your grades. But if I recall, you're only required to have 4 chapter tests on your UVU grade and then your final exam. Okay? So what that would mean, if they'll let me do it, that would mean I would just have, so that means only 4 of your 6 test scores are going to show up on your UVU grade along with your final exam. But keep in mind, your final exam is basically worth twice as much as a normal test. Okay? So if you're excited because a low test score, or maybe 2, don't quote me on the fact on 2 tests being dropped for your UVU grade. Just, I have to see. Might only be 1 test that gets dropped. But a regular test is like 100 points. Your final exam is worth twice that on your UVU grade. Okay? So if there is a test that, you're excited it's getting dropped because you didn't understand what the heck was going on in chapter 5, there's going to be chapter 5 material on that final exam. And that's going to be counting towards your grade, whether that test gets dropped or not. Does that make sense to everybody? Okay, I'm sure it does, but I just want to like really drive that point home. You don't get to just pretend chapter 5 never happened. You've got to go back and practice it and try to get it a little bit better so that you can be successful on the final exam. Okay? I will say from what I've seen so far that the final exam, the stuff that they've sent out saying this is what might show up on the final exam, it's all a little heavy on like systems of equations, like solving big systems of equations like 3x3. Also, it has some kind of tricky stuff with like transformations of functions. They're just asking it slightly different than they did before, so we'll just have to review that a little bit. And then you've got to remember like your rational functions and your polynomial functions, your logarithms. It's been a while since we've done that. So anyway, I will get the stuff out so that you have your chapter 8 review and I have a big review for the final exam that basically goes through all of the topics that you should have learned this year. And then I also printed you just a practice exam that has like 22 questions on it, I think, formatted the same way that they will be on your actual test. Okay? If you come across Cramer's rule or like binomial theorem or binomial expansion, those are the 2 topics we skipped. We have permission to skip them. But if you like are working on a final review or like a list of final exam topics and you see either of those, just know that those are not going to appear on your final exam. Okay? Any questions? We good? Okay, so you all know what's coming up. You know that you have to do stuff on your day that you're not sitting in this classroom. We are all in agreement. You nodded your head. That was a contract. Okay. All right, so geometric sequence. What is a geometric sequence? Well, last time we talked about arithmetic. Last time we talked about arithmetic. Arithmetic sequences are sequences where you're repeatedly adding or subtracting to get the next term and the next term and the next term. So what do you think is the case with the geometric sequence? You're repeatedly multiplying, okay? So the terms of the sequence are created using repeated multiplication this time. So if I start out a sequence at 2, and then I put 4, and then I put 8, what's next? And then, okay, this right here, this relationship between the two terms, in a geometric sequence, this is called, this multiply by 2, this is called our common ratio. What was it called last time? A common difference. Okay? So a ratio, you think about a ratio, if the ratio is 2 to 1, then that means there's twice as many boys as there are girls or whatever. Okay? So it's actually, ratio comes from dividing. So the common ratio is found, 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. Yeah? In an arithmetic, even though we always say we're adding, the term is common difference because we're looking at the pattern. And to find that common difference, we take 4 and subtract 2, and we get 2. 6 subtract 4 is 2. 8 subtract 6 is 2. So we're always going backwards to figure out what the pattern is. So that's why the words are difference and ratio. Okay. Okay, so the formula, let's just do the formula for the one I already wrote on the board. With an arithmetic sequence, you would have your first term, and you would add the common difference, but only n minus 1 times. So you don't add the common difference for every single term because the first term doesn't have the common difference added to it. Okay? This one, our formula is going to look like this. We're going to say a sub n, so a with a subscript of n, so the nth term is going to be equal to a sub 1, the first term, times, what's r? The common ratio, okay? How many times, let's say the nth, let's say we're talking about the third term. So that's 8. How many times did 8, or how many times did 2 get multiplied by the common ratio to give me 8? So it's the third term, but I only multiplied by 2, how many times? Twice. So when I multiply by r, I'm going to say I multiply by r, but only n minus 1 times. Yeah? Pretty easy? Okay, so I could say my fifth term would be the first term times r, 5 minus 1 times. So let's look at it. 1, 2, 3, 4, 5. So 32. Does that equal the first term, 2, times the common ratio, also 2, to the 4th power. Is that accurate? 2 to the 4th power is 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Is 16 times 2 32? Yes, Allie. Yeah. Only because in this case our first term and our common ratio matched. But it's going to be different from here on out. Yeah. Okay, so let's do a different one. That brings up a good point. So let's come up with a different geometric sequence and write the formula. Okay? So let's do 1, 3, 9, 27. Okay, so what is the formula here for the nth term? A sub n, so that's our nth term, a sub n must equal the first term times 3 to the n minus 1. Good? Pretty easy? Okay. So one of the things you will be asked to do, like there are some questions where it asks for the first 4 terms of the sequence. It wants you to find the 100th term of the sequence. Yeah, okay, pretty straightforward. We can also use recursive formulas here. Okay, what does recursive formula mean? Yeah. So for our first example that we had over there, in order to use the recursive formula, I define that nth term based on what would happen. How do I get this one by doing something to this one? Or how do I get 8 by doing something to 4? Or how do I get 32 by doing something to 16? What is it? What do I do to it? Times by 2. So my nth term is equal to 2 times a sub n minus 1. Just the term right before it, double it. Okay, but in order to use the recursive formula, you have to begin by saying what the first term is. So the first term was a 2. Otherwise, you can't start, because if you don't know the previous term, you can't even begin to write out the sequence. Okay? So what would it be on this one? In this one, a sub n would be what? 3 times the previous term. And a sub 1 is 1. Good? Pretty straightforward? Okay. Then we get into partial sums. Let's see. Let me see if there's anything else. Oh yeah, we need to do this first. I lied. Not partial sums yet. Okay, so it's going to be tricky. A little bit of math that we haven't done for a minute. So here's an example. Something like what you're going to see on your homework. It says the third term of a geometric sequence is 63/4. Okay? And then it says the sixth term of that same sequence is 1701 over 32. It wants you to find the fifth term. Okay. I want you guys to get out some paper. You can come grab a whiteboard if you want. Get out your calculator. Whatever you want. I want you to start thinking through this question a little bit. So find the fifth term, but then I want you to be able to write the formula for the nth term. Allie. Usually I wouldn't care right then because I just said do it, but your book will always want explicit. That was a good question. So your book is not a huge fan of recursive sequence or recursive formulas. Okay, so somebody share with me how you went about finding the value of the fifth term of the sequence. How did you do that? Silence, yes. Allie. Okay. So you're looking at like here's a 4, and then there's a fifth or a fourth term, a fifth term, and then a sixth term that was a 32, kind of like that. Okay, so that would help you with the denominator. So what must you be repeatedly multiplying by in order to get from 4 to 32? 2, because if I multiply this by 2, I get 8. Multiply that by 2, I get 16. Multiply that by 2, I get 32. So that means my common ratio must have a 2 in the bottom, right? Then they went and looked at the top, which is a little bit uglier, starting with a 63 at the third term. There's a fourth term we don't know, a fifth term we don't know, and then our sixth term is 1701. How did you even know what to try? Okay, so like a guess and check approach. Did anybody do it any different? Just curious. Isn't it true that to get from here to here, I would have to multiply by that common ratio a grand total of 3 times? So could we say something to this effect? I have to multiply by something 3 times to get to 1701. Do you guys know how to solve that equation? I think you do. What's 1701 divided by 63? So x cubed has to equal 27. So what is x? 3. Okay. At this point, because the third term and sixth term weren't that far apart, maybe that like guess and check approach is going to be fine. But at some point, those two terms might be like 22 units apart or 22 places. I don't want to do that. I don't want to guess and check and have to type into my calculator 22 times. I mean, I guess I could use an exponent, but yeah, I don't want to guess and check every time. So a more straightforward approach, which if we use this straightforward approach, we didn't necessarily have to split up the denominator and the numerator. We could have done it all at once. Okay? So r ends up being 3/2. How does that help us find the fifth term? So what do I need to do to find the fifth term? Do I know the first term? No, because I don't know the fifth term, I can't use this traditional equation, right? But if I found the first term, I could. Or I could just say, well, kind of like a recursive approach to the problem. If I already know the third term, then the fifth term must be the third term times the common ratio twice. Because multiplying it once by the common ratio would give me the fourth term. Multiplying the fourth term by the common ratio would give me the fifth term. Yeah? Okay. And what does the fifth term turn out to be? But then I come back and say, no, I really do want the formula for the nth term. So you're going to have to find that first term for me. How do you do that? So if you've got your third term, you could divide twice, right, by the common ratio. Okay. In a formula, though, let's just make it super, super clean cut. In a formula, I would have the third term equals the first term times the common ratio twice, right? Because the exponent is 3 minus 1. Okay? So if I know that the third term is 63/4, but I don't know the first term, but I do know that the common ratio is 3/2, can I solve that equation? Again, as opposed to like a guess and check or just like manipulating approach, try something like this. So then 63/4 equals the first term times 9/4. How do I solve? Divide both sides by 9/4. What does it look like when I divide a fraction by a fraction? What do I need to do? So I'm going to take 63/4 and multiply it by 4/9. 4 goes away. Does 9 go into 63 nicely? Yeah, what is it? So what's the value of the first term? 7. Would you have looked at those two numbers and automatically decided that the first term was a 7? Kind of weird, right? Fine. So the formula then for the nth term, for any given term, the formula is first term, 7, times common ratio, 3/2, n minus 1 times. You feel okay about all that? Solid? Excellent. That's a good word. Okay. All right. Let's look at I don't want to do it that way. Okay, there was one other way, one other option for solving that, but I don't think we want to go there. Okay, so the next thing we need to talk about is partial sums. How many have already looked at the arithmetic sequence stuff? Any of you? The 8.2, section 8.2. Okay, so the arithmetic sequence or the arithmetic partial sum formula comes from a little story about a little mathematician, but when he was in elementary school, he got into trouble, and his teacher basically wanted to give him a timeout and told him to just sit down and just add up all the numbers from 1 to 100. Okay? So we use that story in the way that he was able to quickly come up with an answer, like in your face, little elementary math teacher. This kid knows what he's doing. So he was able to, within a couple of minutes, decide that the sum of the numbers from 1 to 100 was 5,050. And he was right. But he didn't have to write down on his paper 1 plus 2 plus 3 and figure all of those steps out. He figured out a smarter way to approach the problem. That's where our formula came from. So that formula to me makes a whole lot of sense. Okay? The formula that I'm about to give you, not so much. Okay? What we call derivation in math, how we derive this formula, is much more complicated for a geometric sequence than it was for an arithmetic sequence. So, because of that, because this is our last day and we've learned a lot, we're not going to go into the fancy derivation of the formula. I am going to give you the formula and you have two options. 1, you trust me. 2, you look up the derivation and watch a YouTube video about it. You feel okay about those options? Okay, it would take more than the time we have left to do the derivation. So I feel like that's a little bit of a waste at this point where we have such limited time together. All right, so I'm just going to go back here, give you the formula, and then show you how to use it. And then hopefully you will still have faith. Okay. You do not have to memorize this formula. It will be given to you anytime you need it. Okay, so that notation looks familiar, yes? This notation says the sum of the first n terms, okay? If you know it's a geometric sequence, then you take the first term, multiply it by 1 minus r to the nth power, so your common ratio, and to the nth power that matches this number, okay? So if I was trying to find the sum of the first 4, this would be a 4. Divided by 1 minus r, okay? So, with that formula being given to you, can you find so I already threw a wrinkle into the system, but I think we can push through it pretty easily. The wrinkle being what? If I need to find the partial sum, when I go to write that formula down, that means I'm finding S sub what? I don't know. I know I'm supposed to add the numbers from 1 to 4096, but I don't know what term 4096 is. Yeah? So the first thing I have to do is figure out how many terms there even are in that particular partial sum. Okay? How? I have a question. What do you know? Looking at just that, what do you know? Yes, your common ratio is 4. Anything else that you know? What's another thing that we need to know a lot of the time? We have a first term, okay? So we know that our nth term is going to be our first term times the common ratio raised to the n minus 1, correct? Okay, can we fill in the blanks with what information we do have and see if we can use that equation to help us solve for what we don't have? So our nth term is what? What's our nth term? What's the last term? 4096. What's the value of the first term? What's the value of r? What goes up here? N minus 1. I don't know what n is, so I can't actually carry out that subtraction. But how many variables are there in that equation? Just one, so I can solve for it. Question is how? Well, I don't really need the 1. If I had something besides a 1 right there, I would divide both sides. I'm actually going to write that out, even though that looks really stupid. Because if that was anything besides a 1, you have to remember to divide by that number first. Okay? So I get 4096 equals 4 to the n minus 1. Friends, how do we solve for exponents? We use logarithms. It's been a minute, huh? Can you rewrite that exponential equation in log form? How? Log base 4 of equals n minus 1. Does anybody remember how to calculate that? So many people talking. So so many exciting news and what is it? Log of 4096 divided by log of 4. Change of base formula, if you will. Look, we're reviewing for our final. Good for us. Okay, that is going to be equal to n minus 1. Okay, throw it in your calculator. So, if you take log of 4096 and divide it by log of 4, and you get 6, is your answer 6? No. So 6 is still n minus 1. So what is n? 7. So what did we just figure out? How many terms are there in that sum? 7. We are adding up the first 7 terms. So let's see if our formula will help us now. What's this? 1 times what? Oh. Just seeing if you were paying attention, that's all. Not even a real R, like a super crappy R. Okay. All right, let's see if you have the calculator skills required of you. Can you get the correct answer out of that? So much pressure. When you think you have an answer, shout it out. Okay, it is 5,461. Is everybody okay with getting to that number from that calculation? So what is that number? What did we just find? That is 1 plus 4 plus 16 plus 64 plus 4,096 equals 5,461. Good? Pretty easy? Okay. All right. Then that's about where we would have ended with arithmetic. That's all we had to know about arithmetic. But with geometric, there's a special situation. If you have an arithmetic sequence like 1, oh, it doesn't even matter. We'll just make it super simple. Say we have that arithmetic sequence. Can we find the sum of all the numbers in that sequence? Do you see the dot, dot, dot? Where does it end? It doesn't. So can you find the sum? So if you think about it, if that sequence goes all the way to infinity, then you're adding infinity with infinity minus 1 plus infinity minus 2 plus infinity minus 3 till you find a number in there somewhere and then add them all until you get down to 1? Yeah. But then there's always another one. You can always add 1. That's what this sequence is doing. So whatever number you determine as infinity, I can add 1 to it because I'm a smart aleck like that. Okay, I can always add 1 more to whatever number you think is the end of that list. So therefore, you can never, ever, ever find the sum of that sequence. Yeah, even if, so we think maybe it's just because those numbers are so big, or maybe it's because they're all positive. Even if I gave you this, it's not arithmetic, but another sequence. I mean, this negative 2 and that negative 4 and that negative 6, they're kind of canceling things out for me a little bit. But does the sequence ever end? Can I ever find the sum? No, because the numbers are continually getting larger and larger and larger and larger. Okay? And even if they were getting smaller, like it's just more negative, so it's still impossible to add them all up, okay? But with geometric series or geometric sequences, there will occasionally be cases where the numbers are moving in such a way that you could actually find the sum of an infinite list of numbers. Okay, I'm going to give you an example. I like cake a lot. You ever need an A? I like cake. Anyway, so let's say I buy myself a cake because nobody took the hint and bought me a cake. So I buy myself my own cake. And I tell myself, Jamia, excuse me, this is McMurdy, you need to show some restraint. You are only allowed to eat half. Okay? So on day one of having this cake sitting in my kitchen, I eat half of it. And then the next day, again, the rule is I can only eat half. So how much cake is there left on day two? There's a half left, so if I eat half of that, I'm eating a fourth. That's disappointing. Wow, okay. You didn't even have to think about it? You just know? I have a question. I have very precise cutting and measuring tools, just so you all know. Okay? So on day one, I eat a half a cake. Day two, I eat a fourth of the total cake. Day three, I eat an eighth of the total cake. Day four, a 16th. Day five, I reward myself at the end of a really shizzy day with 1/32 of a piece of the cake. And I keep going until I run out of cake. Do I ever run out of cake? Theoretically, in the math world, I never run out of cake. This is my world, Maggie. Step into my world where all we do is eat cake. All right, so I have the tools to make it possible to find minuscule fractions of my cake so that I can continue enjoying it despite its staleness. Yeah? I have a question. In the end, how much cake did I eat? In the end, add it all up. How much cake did I eat? I still ate Uno cake. 1. I add up all of those up to infinity. So on the infinitive day, I made that up. I had an amount of cake so small that I cried, and then I was done. I ate the whole cake. I ate one cake. Is this a geometric sequence? What is the common ratio? Can I add them all up? Can I use this formula? What does this formula require of me? A first term, do I know it? It requires an R, do I know it? And it also requires an N, do I know it? There's a dot, dot, dot. There is no N. This is what we call an infinite geometric sequence or series. If I replace all of the commas with plus signs, it's technically called a series. Okay? But this one's infinite. It's going on forever. So I can't use that formula over there anymore. I need a new formula. Yep. Nope. Let's try. Ready? Let's see if this one works. No, this one will also be on your formulas. Why? Why? No, that's a mix between a 1 and an R. It's just supposed to be a 1 and then an R. Okay, looks pretty simple. Do you think it's really that simple? Let's take a look. What's our first term? What's our common ratio? What's a half divided by a half? How much cake did I eat? One cake. What do you think? This is the only like real life semi-logical application of this formula that I could come up with. That's why there's a rule. That's why I have to tell myself I'm only allowed to eat half, because otherwise, she gone. Okay. All right. So, will this work with any geometric series or sequence? So I told you up here, I gave you some examples of things we could not add together because they go on to infinity. Okay. Could I add this one together? All the way to infinity? Can I? The way that I was able to do that one? 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus what? Plus more. I can take that infinity and I can double it because I want to. And then I add that one. And then I double that one and I add that one. Does it make sense to you that this one is not possible? I cannot find that sum. So why am I able to do this one? What are they doing? They're getting smaller. If they're getting bigger, then they just keep getting bigger. This list of numbers is actually approaching what number? Yeah, at some point on some day, I kind of sort of just eat 0 cake. And then I'm done. Right? But with that one, if I allow myself 2 chips on day 1, 4 chips on day 2, 8 chips on day 3, how many chips can I have in the end? I don't know. I can't count that high, and my stomach is not that big, and I don't like to vomit that much. So that's not happening. Okay? But does it make sense to you that I can't even like quantify when to stop eating the chips? Do any of you have that issue? You don't know when to stop? Depends on the chip, right? Okay. But because this one has numbers that are approaching 0, eventually I get to the point where I can add them all together. So, when does this formula work? When you see this sequence or this series, so sequence if it's got commas, series if it's got plus signs, when you see that it is decreasing to the point where it is approaching 0, not decreasing like to become more negative, decreasing as in approaching 0. Okay? All right. What else do you need to know? Christmas egg hunt? I love it. I think everybody should get all caught up, like ASAPO. I just want to put a little vocabulary to this really quick. What? No, not really. They can only hear like what talks right into the microphone. I don't know that there's anybody listening today though. But when they watch the video, Yeah, they can only, I think they can only hear me. Okay, so if, what's this R? The common ratio. So it doesn't matter if it's positive or negative. That's why there's absolute value bars on it. So if that number is less than 1, aka it's a fraction, right? Like 1/2, 1/4, 1/3, something like that. So if it's less than 1, then the infinite geometric series, we use this word, converges. Converges. And has the sum S equals A over 1 minus R. Okay, but if R is, what's the other option? Greater than 1. Then you imagine the numbers will keep getting bigger and bigger and bigger, right? Anything bigger than 1, even if it's only like 1.2, doesn't matter, it's still bigger than 1. Then the series, what's the word? Diverges. It has no sum. Okay. All right, so your assignment, this one's a little bit beastly, so I would not put it off. So it's going to start on page 614. You're going to do 5 to 25, the odds. 29 to 45, every other odd. And 49 to 75, the odds. And 76 to 233 all. Just kidding. Just kidding. Okay. So, last lesson. Any questions about geometric sequences or series? Does that final piece make sense, that they only have a sum if they're getting smaller as we go? Okay. Yes. You just say it diverges. No sum. Can't add them up if it diverges. It actually says in the instructions, say if the series converges or diverges. It's right there for you. Yeah, you think about like converging, it kind of sounds like merging, like you're becoming, you can, this can happen. But diverging is like, whoa, it's not possible. Okay? Good? Any other questions? We should in about 5 minutes.